Hello everyone again and welcome to the DMSI YouTube channel, and it's truly a pleasure to actually have you all in this particular space. Now you're coming here of course seeing the particular title and the thumbnail, collisions with respect to momentum. How does that actually work? Momentum, everyone talks about momentum all the time. It's like, oh, this person moved at momentum, that is why this person slid and fell. Kind of interested to see how that is actually placed in that particular concept. But when it comes to looking at context behind momentum, this is where we actually go to look at our goal for today in terms of the keywords. What it is means when you're talking about linear momentum. What does it mean when you're talking about impulse? How is this applicable to the laws of conservation of linear momentum, and also how that connects really well to the elastic collision, which is the opposite of inelastic collision, and how you can have completely inelastic collision happening in various objects when they are in contact with each other. Various interesting formulas will also be addressed, and all these formulas are really important because they are really rightly connected to the mass and the velocity as you observe. So first is the following. Linear momentum, we all know, is when an object is actually having the mass and is subjected to velocity. Now take note that the product of the mass and the velocity of that object, take note that this shows that yes indeed momentum is the vector, which means it's a vector quantity, which means that it has a magnitude and a direction, so you need to take into account that. And by looking at the SI unit of momentum, you actually figure out that since mass SI unit is in kilograms, we know that the velocity is in meter per second. Therefore, bringing those together gives you kilograms meter per second. So now we've taken care of that, we can also look at how we can build our momentum in terms of how impulse actually plays out. Impulse is given to an object where, in this case, the product of the net force of that object at a particular time interval gives you, in a way, the change in momentum. And you can indeed derive this particular formula by first knowing from your Newton's second law of motion that the net force on an object is the mass of the object times the acceleration. By changing acceleration to change in velocity with respect to time, we do know that, hey, we have change in velocity over change in time, move change in time over to the other side of the equal sign. That means that you have your net force multiplied by the time interval that that object is actually having contact with a stationary object usually. And while on the other side of the equal sign you have the mass of the object multiplied by the final velocity minus initial velocity, which we know to be called the change in velocity. So in conclusion, this actually on the right side of the equal sign tells us that, hey, indeed this particular right side of the equal sign is rightly similar to momentum, and in this case here it is shown to be called the change in momentum. Now speaking of impulse, impulse here has a unit which is rightly similar to momentum's formula. The only difference here is that that particular grams meter per second actually is gotten from Newton seconds, where Newton is measured in terms of the unit, or broken down to be mass times acceleration. Acceleration is meter per second squared. If we cancel the seconds squared at the bottom, one of it, to the seconds at the top, you can actually go back to the derive the momentum formula. So it depends on how you approach this, and there are many examples of how impulse actually is applicable. Like for example, you have a particular baseball thrower throwing a baseball at a particular pole. That contact between the ball moving at that particular force or exerting a force on that pole and the time the ball is on that particular pole before it moves in the opposite direction, that is called impulse. So that time interval of contact before touching and after touching, so that is the immediate seconds. It's usually in milliseconds, and it's quite interesting to see how various examples in the textbook or anything that you will be encountering is going to be addressing that, which actually leads us to momentum in terms of one dimensions. Now take note that as long indeed that the law of conservation of momentum plays out, if there is a net force that is equal to 0 in a system, it means indeed that momentum is rightly conserved. And so during interactions either with one object or another object, when one object is moving and another object is stationary, you can actually have momentum which leads to collision, and that is where this actually comes into play. Take note here that object 1 changing momentum and object 2's changing momentum is the same or equal to each other, because conservation of momentum is actually at play, but they are opposite in direction. Because in here you have object 1 coming at, if you assign this to be positive, to the right, and on this side here object 2 coming in contact to the left. That means negative velocity, positive velocity, and in there you have that particular momentum established. And in this particular case here, you can actually rearrange the equations in such a way that you can move all the before collisions velocities over to the left side, which means that you have object 1 and object 2 in terms of the mass and their velocities sum, and on the right side you have the mass of object 1 and object 2, but in this case you have final velocities of object 1 and object 2. So in this particular case here, we see that you can actually go from that original formula where negative momentum is equal to positive momentum for object 1 change and object 2's change, and that can lead you to an expanded equation where it can be easy for you to actually play around with all these wonderful questions that comes into play. Now, following up on particular forms of collisions, we do have 3 different types of collisions. We have elastic collision, inelastic collision, and completely inelastic collision. Now, taking note that all these 3 collisions, momentums are indeed conserved. However, looking at the kinetic energies, there are differences in there. Like for example, we have elastic collision where an object comes to contact with another object and you have the equal amount of velocity, which leads to equal kinetic energy before and after to be established. However, when we look at inelastic collision, some of the energy are lost in terms of kinetic energy after. So before kinetic energy will be more than after kinetic energy, either in form of friction or in form of various form deformity in terms of the object. That could be a way by which a specific inelastic collision can be accomplished. And finally here we have completely inelastic collision where you have object kinetic energy before to be way higher than the after kinetic energy to the point of minimum, and usually in that case the 2 objects after collision, they stick together, and that is how that plays out. Now take note here that in terms of how you'll be solving questions, you should recognize that you'll be doing systems of equations where on one equation you're going to have the main momentum equations for before and after collision, and for the second equation you're going to have the kinetic energy before equals to kinetic energy after collision. So take note of how to approach questions like that, because that comes handy as we move to other types of questions which will involve 2-dimensional momentum or collisions. So really fascinating to see how that plays out. And there are some cases where a question can come to your mind in terms of, or come to you in terms of, hey, if you actually have a specific situation where 2 objects, they have the same mass, what is going to be the velocity? In this particular case, it's really incredible, because when you're solving your problems using your collision momentum before after equation 1, and in this other case here you have kinetic energy before and after, you have those 2 equations, what you realize is that the masses, they all disappear, because that is independent on the masses. It's not dependent or not dependent on the masses, because both masses are equal, mass 1 and mass 2. But what happens is that there is going to be a switch in the energy in terms of the kinetic energy, and also in terms of the velocity, because what happens is that object 1, assuming you have elastic collision moving and this body here is stationary, that is the other condition, what happens is that this body completely transfers its energy over to this. Therefore, this energy or velocity of this object stays stationary after collision, which means velocity after for object 1 is 0. However, this body obtains this object's kinetic energy fully, which means the velocity of this object will be equal to the initial velocity of this object. Therefore, in conclusion here, we have a complete transfer. That is a proof that yes, we do have a specific elastic collision of an object where these two objects, one are in this case having the same mass, which means mass is independent here, and secondly, one object is stationary and the other object is at motion. So velocity is transferred completely from object 1 to object 2, and that is how this actually plays out. There's some other places, like for example, you people that love to play curling, good for you. When you roll a particular coil, I don't know how you call that, but what the object is called, but when you roll it on ice, depending on what position you want to hit the other object, sometimes you can hit it at the center, at the middle, but sometimes you can hit it a little bit far away, which means that there will be angles that will be created as a result of that, which means that you want to be able to recognize at the end that the velocity component is going to be at play, but overall the same concepts that you are going to be approaching in terms of the specific change in momentums before and after will be applied to that scenario, as well as the kinetic energy. So it's really wonderful to think about this in terms of how momentum actually works in terms of collisions and also in terms of conservation of linear momentum. And I hope you found this really informative in not only terms of how to use the equations, what the equations mean, but also how it's applicable to the real world in terms of sports or all your daily life activities. All the same, please hit the comment down below. Let me hear your thoughts about this. The notes is actually found on my website. You can check the notes out, and also in terms of various interesting other videos that will be coming up soon, I will encourage you to check those out. But all the same, stay smart as always and believe in yourselves.